welcome back from the break. Over the next hour, we're going to be discussing testing. We'll move through code coverage, I think, probably fairly quickly, and then we'll end up with continuous integration. Before I begin, I want to extend thanks to Alicia Klinvex. So in previous AppPetsk events, she was the one who would have been giving this talk, and as such, I inherited her slide deck and much of the flow of this talk from her. So clearly, I'm indebted to the work that she had done. As part of what Alicia had done and what I inherited were those same three examples that Anshu went through. In the interest of time, making sure that we get to the continuous integration portion of the talk, we decided to move those off. So I'll pause for a moment to say that I am a giant nerd. When I inherited these slide decks, I went and I really started researching these to try to understand why these failures occurred, really understand the lessons learned that people have drawn from it, and then try to understand how I, working in perhaps a different type of software development, might really benefit from what was learned from those discussions. So all that to say, I'm going to skip over them now, which is probably very good because that would have been a very lengthy and boring conversation. But however, if anyone is interested in discussing those in more detail, in the hands-on portion after the dinner, I'm more than happy to talk about this, about Git or Git workflow, or anything related with testing. So please come up and find me later if you are interested in any of that. So we'll move past those. And then I'm going to start off from this very same quote that Anshu had about programmers inserting bugs into code. The point for me here is that because we are responsible for putting the bugs into the code, perhaps what we should do, according to this quote, is actually invest some upfront effort to make sure that we don't put them in there in the first place, right? So we'll move on to a second quote, this time by Brian Kernighan, which says that debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it. Right? So this only seems tangentially related to this discussion because what it's really saying is don't write clever code. But one of the reasons why I like this, included this, is because it's essentially a mathematical proof, but founded on this apparently commonly understood statement that debugging is twice as hard as writing the code. That's something that we all understand, right? And so if we couple that with the previous quote, maybe what we can understand is if we do put in some upfront effort and we avoid putting bugs in, then we'll also make our lives easier because hopefully we'll never have to do debugging again, right? Really, the idea of upfront effort here can make our lives better in the long run is what we're talking about. So what might that upfront effort look like? A wild guess, it might be testing, right? And so hopefully when you guys are actually building some kernel or you're writing some difficult code, when you get to a point where you think it's done, you're going to sit down and put some effort into actually conceiving of a test case. This is what Anshu was talking about a bit. This can be a very difficult part. You need to think of a problem related to that solver. You need to come up with inputs. You need to think of perhaps numeric configuration values. You also need to conceive of the expected output and perhaps a tolerance. So you'll go through, you'll sit down after you've conceived of that test case. You'll actually put it through your software, collect the outputs, compare it against this expected output, and compare it and consider that against the tolerance to determine whether or not what you've done is correct. That is a challenging task. It's great that you've done it because that means that you really are working towards this to avoid putting bugs into the code. But the idea is, why don't I actually take that a step further and put forth a little bit more upfront effort and take that test case and actually put it into code form and package it up next to my code. In other words, what I'm talking about is integrating those test cases, those inputs and outputs, and package them up in the same repository as your code. Really try to take advantage of all that value and of that time and effort that you put in. And if you do that, then clearly if you go back and work on that code a little bit later, well, you'll just recall that you already have that test and run it and be done. And also if other people are working on it, then they can benefit from that effort that you've done, right? That's a very good thing. And so all in all, hopefully, that will ease the process of debugging, if not actually preclude it. Another benefit of having tests integrated in with your code is that oftentimes they can form as a sort of tutorial or actual documentation. People can see how you intended to call your code and use it. So benefits of testing, promote high-quality software development that first and foremost delivers correct results and improves the confidence in what we've done. But if people actually go back and look at the tests and see that I'm putting in a high level of testing, hopefully that will convince them as well that I have written some high-quality code and that they should probably use my code. So we hope that it will increase the quality and the speed of development. If we do integrate tests with our code and we decide to use our software on a different platform, well, then I'll migrate my code over, build it, run the whole test suite. If I don't find a failure, great. I know that I've got portable code. If I find a failure, well, I'll go and change my code until all my tests are working, in which case I've grown my code, I've improved it, and now my code is more robust. Finally, and this is more sort of a personal opinion of mine, is as I've used automated testing, I find that I write code that by definition can be tested, for instance, and therefore I try to avoid writing what I would call brittle code. And so what I mean by that is code that's so difficult to read, so complex, so difficult to use, that no one wants to possibly stick their fingers inside, because they know that no matter what, how small of a change they try to make, it's entirely possible that they might break it and create a bug, and in the worst case, that bug goes undetected. So let's work through some definitions. We already saw this quite a bit in Anshu's talk, but so I won't go into depth as much as I normally would. But if you imagine a piece of software that you work on, and then you go a step further and imagine the entire universe of tests that you could possibly write for your code, well, how can we partition those classes up into, or those tests into different classes? So one classification scheme would be by granularity, as Anshu had talked about. And when we do that, we hopefully will have a test suite with a hierarchy of granularity. So at the finest granularity, we have unit tests, which I imagine most people have heard about. When we write code, we write individual functions and classes. And when we do that, we're first specifying an interface. And when we specify the interface, we're establishing a contract. If you give this function or this class this data, then this is the output that it will give you. And so we can write a function or a class that's a unit test that's related to every function or every class that could simply test that the implementation that we've written, that it actually satisfies that contract. One of the nice things that I find when I'm writing unit tests is that one of the first things I will think about as I'm writing them is what are the edge cases, right? I don't want that to be an afterthought. When I use unit tests, that's oftentimes the first thing I will think about. So as Anshu said, these are generally lightweight. They run very quickly, so therefore they're probably a developer's favorite tool. But just because we've got test functions and classes in our code, and we've tested them all and see that they're all functioning, of course, that doesn't mean anything, because the programs that we're going to write are not simply a decoupled collection of functions and classes. Rather, we need to couple them together into larger components and subsystems. And so when we start to assemble them, we create the functions and the classes, we link them together into higher functioning units, we create these components or subsystems. In a similar way, we're also going to understand that there's probably an interface to that subsystem, so a contract, and therefore we can write this sort of higher level, a bit more coarse component subsystem or integration test where we're making certain that that assembly of higher functioning units is actually achieving the contract again. So you can imagine that now here, the unit test, the test cases might be fairly easy to conceive of. At the component level, we might need to do a bit more tricks. We might need to think a little bit to come up with a good test case, or perhaps ones that's simple to understand, easy to implement, and easy to maintain. At the lowest level, or the coarsest level of granularity, we have system-level tests or end-to-end level tests. This is where we're really testing at the experience of the user of our code. So at one end, we would have the inputs to the problem. We would have the configuration values. At the other end, we would have the output that it's created. And so you can imagine here that this is going to be using probably exercising a higher fraction of the lines of code in your test. These tests could take a very significant amount of time, but they're nice because they're hopefully going to be a high-stress test, and they will hopefully catch subtle bugs in the system that perhaps you don't see with a unit test or a subcomponent test. So let's try to imagine why we like having this hierarchy. So let's say I do have a system-level test that I run and that detects a bug. It might be very hard for me to just look at the failure and think about what this system-level test is doing and immediately zero in on where the bug is. So what I'll probably do is jump up to a finer granularity and start running component tests. I can probably make an educated guess about what subsystems might contain the failure. and these will be a little bit faster to run. So hopefully I can run more of those and immediately figure out what subsystem contains the failure. And then I can start to look at its constituents and run the very fast unit tests to hopefully find out which function or class is failing, and then use that test to make sure that I've actually fixed the failure in the first place. So another classification scheme that we can imagine is the classification of tests by intent. Why am I running this test? What do I care? So the first most obvious class would be general verification. So for instance, if my software is capable of working on a particular model that's simple enough that there's a known analytic solution, well, I'll take the inputs, the configuration values, take the output and compare that against the analytic result. Everything's fine. I might have a case where I don't know the analytic result, but there is an independently designed software that can also solve that problem. So perhaps in this case, what I can do is take these two different softwares, run the same problem in them, collect the outputs, and then make certain that those two outputs are close enough to each other within a certain tolerance. Another class would be the regression test, which is extremely useful as you're developing. In this case, a domain expert or an expert in the software will sit down at a point in time. They'll look at the software, they'll look at this particular test case, and they'll deem that the software in this test case are functioning. They'll therefore run the problem, take the output, and store it somewhere as a baseline or a gold standard. And from that point forward, as I'm developing, I can occasionally pause, run that exact same problem through my regression test, take that output and compare it to the baseline. As long as it's within a certain tolerance, then I haven't broken the code. It's important to emphasize here, though, that just because I'm getting a passing regression test, it does not necessarily mean that the code is actually functioning. It might be at the point that I establish the baseline, either perhaps I know that the code's not broken, but it's a reasonable output for the current state of the development that I'm doing, or perhaps I simply cannot know ever that it's correct. The point is here that when we do the regression test, we're doing a differential testing between what I'm currently generating and what I was generating in the past. So if they don't match, that means there's been a deviation or a regression in the code and I broke something. Finally, we have, for instance, performance tests. So here I'm not looking for the correctness of my code, but I'm going to just actually run it and see that the code is running as expected in terms of runtime. I'm also going to check to see, for instance, the resource utilization is as I imagine or as I need. And then finally, we have these restart tests, which Anshu has already spoken about. So let's put these definitions and our notions of testing to use. We're going to go through this toy workflow that I built up in terms of refactoring. We've already heard the definition of refactoring by Anshu, so we can skip over that a little bit. When we start looking and analyzing this workflow, we're going to imagine first that we have a piece of code that is functioning correctly. We like its behavior. And at the same time, we're going to imagine that we've already integrated a rather full set of tests in our test suite to be able to continue with its refactoring. One of the natures of refactoring is that we're probably not going to try to do the refactoring in one push. Rather, what we're going to do is break the refactoring down into several different little steps. We'll implement one and we'll test to make sure that that refactor step was correct. And so here we take our first refactor step. We've identified some regression or unit tests, some lightweight, fast tests that will test the functionality that I'm messing around with, let's say. If those fail, well then my refactor step was bad and I need to go back. And so I'll keep iterating between implementing the refactor step and testing that I didn't break anything or change the behavior until finally my tests pass. And then I have to ask myself, was that the last refactor step? If no, then keep repeating through those cycles until finally I've done all the refactor tests and all the associated tests that I've run say that I did that correctly. But here we were using fast, lightweight tests. They're probably limited in scope. So I only know that I've really not created a bug in one particular part of the code. So I'm going to not say that I'm successful yet. I'm going to sit down and now use those heavier weight, high stress tests that are going to take a little bit longer to run those through. If I identify a failure, well then I have to go back. And now I've got a bit more of a challenging problem because I don't know which refactor step was the problem, but I can just keep using those and iterate through until finally all of my tests say I'm successful and I'm happy with my refactoring effort. So up to this point, we've been imagining that tests have been done in a manual sense. But as you heard from the last talk, and I'm sure everyone would like, we would like to be able to automate this as much as possible. And you can imagine that as you're running these tests or designing them, the design is probably going to be, of the test suite or the actual test that you're going to run, they're probably fairly similar from each test to each test. In other words, there's probably a fair amount of boilerplate code that exists in running the tests and doing this automatic check between my new output and my expected output. And so this code, because it is boilerplate, does exist in the frame of automated testing frameworks or testing harnesses, as they're sometimes called. So these are software packages, for instance, that provide routines that reduce the tedium of writing test conditions. And what I mean by that is we're going to be actually automating the process of checking my actual output with the expected output. So oftentimes these testing frameworks will have a set of routines like assert equal, assert true, assert false, assert almost equal. So at some point in my program, I'll stop and I'll say, well, at this point in time in the program flow, the variable a should be true. So I'll insert a line that says assert true a. If it is actually false, then inside the testing framework will increment a counter saying that I've run a new test, and it will say that test failed. If it's true, then it will say you did a new test and it was actually passed. So it's doing this bookkeeping underneath for me. These frameworks, they also generally make it easier for you to maintain, so to actually create, maintain, and build the testing suite, and to automate running a collection of these tests in your test suite. And finally, at the end, they will generally report this nice, give you this nice test report. So it will say that you ran 100 tests, of which 10 failed. If it's a particularly nice test suite, it will actually say the failure, one of the failures happened in this file at line 100. A should have been 1, but it was -1, for instance. So that can be quite lovely. There are a lot of different automated testing frameworks. So here's a list of some of them. This is certainly not comprehensive. For instance, for the C++, to the best of my knowledge, these are probably some of the 3 most widely used testing frameworks. So I want to emphasize at this point, though, that the automation is really just checking the present output against the expected output. So at least I'm not having to do that comparison manually. I can just press a button and I get, pass or failed, which is quite nice. However, I'm still choosing when to run the tests. So we can consider another layer of automation in the form of test servers or build servers. And these are servers that automate the execution, actually the building and the execution of the test suite are a subset of the tests in my test suite. You can run them, you can configure them to run on different environments, and in some cases multiple environments, multiple compilers. In general, they host a very nice interface for viewing the results and the history of results. And importantly, they allow for configuring when the tests are run. As you're developing and, for instance, working with a version control system, perhaps you wanted to run, trigger a build and test cycle every time you put a commit on master, for instance. So examples of these would be ctest, cdash, Jenkins, and then these Travis CI and GitLab CI. So I don't need to talk about this too much because this was covered in the last talk. But the idea is when we have the code and when we have the tests integrated in the repository, we do have to maintain it. We don't want them to diverge. And so there's a couple of ways you could imagine this. You might have dedicated team members who are sitting down and watching the tests, who are running them every now and then and perhaps putting some big effort once a month to make sure that everything's clean. However, I would hope that we could start to come up with workflows or just adopt practices in our day-to-day coding whereby it's natural for us to maintain the tests. It's just something that we think about. And so I think I'll give you an example of what that might look like in a couple slides. So here's a reason why you might need testing policies. So if you are using regression tests, which are extraordinarily useful, you have to take the time to establish a baseline, and at the same time you need to establish a tolerance so that you can determine when the new output is too significantly different from the expected output of the baseline in this case. And so determining that tolerance can be quite difficult. It can be a strong challenge. So in the obvious case, if I make the tolerance very wide, then my regression test might be insensitive to bugs that do yield incorrect results, but they're not that far away from the baseline, let's say. So I would really perhaps have undetected bugs in my system if my tolerance is large. However, if I make it too small, then what might happen is I've made a change to the code where the round-off error has changed a little bit. The difference in the new round-off error compared to the last is going to be above this conservative tolerance, and therefore tell me that there was a regression in my code. In that case, I'd have to sit down, look at all the changes that were made in the version control system since the last time I successfully ran the regression test, and determine that those changes were actually correct. There is no bug. They just lead to a sensible change in the round-off error, which sounds like a less than fun task. If you're lucky and you do have the capacity to run your code so that it gives you bit-by-bit exact answers every time you run it, then you can have the option of actually setting the tolerance to 0. In other words, you're going to have a very severe regression test. You're going to demand that you get bit-by-bit accuracy every time you run this regression test. That's very comfortable. It's a very good safety net to have. But the problem is here that, again, when I make the changes to the code that lead to a slightly different round-off error, I need to sit down, look at the changes that were made, determine that the level of change in round-off error that I have is acceptable and in line with the changes that I made, and therefore determine that my new output is my new baseline. In other words, we need to keep a history of the baselines. And so that can also be challenging. Here's another example, and this is going into a little bit about the idea of co-evolving your test with your code. If you have a very large, complex code, highly flexible, highly configurable, it's entirely possible that even though you have a very good test suite, that test suite will not be capable of detecting every possible bug that could occur in your software. So you will find yourself occasionally in the unfortunate situation that you have someone reporting a bug, despite the fact that your test suite says that everything is fine. So the question is, how should we as developers and members of a development team advance with that? I think what we would normally do is just get our hands dirty, jump into the code, figure out where the bug is, and fix that. But what we can do is actually step back a little bit and ask ourselves first, why is it that the test suite didn't actually detect the bug? And take care of that first. So the first thing you could do is study the test suite, and I can imagine two ways that this might have happened. One is that no one ever wrote a test that could actually catch that bug, in which case you should probably write that test. Another case would be that someone wrote a test that could catch the bug, but that it simply isn't catching it, in which case you need to fix that test. In either case, you just keep going and iterating around until the test that should catch the bug actually does and tells you that there is a bug in the system. At this point now, you have evolved the test suite. Your test suite is larger, and as we've heard people mention a couple times, this has the very nice benefit that if anyone ever makes that same bug in your code, well, you're guaranteed that it's going to be caught immediately by this test suite. So once you now have your test suite catching this bug, then you go and fix the bug, right? So if you could get everyone in your team sort of adopting this sort of conscientious work of co-evolving the test and the code on a daily basis, then hopefully the idea of maintaining the test suite is not so onerous. So we can move on now to the idea of code coverage. This is fairly simple. The idea is I've got code, I've got a test suite. That's already very good, but I need to get some idea of how much or what percentage of the executable lines in my code are actually being tested, used, or exercised by this particular test suite. So for instance, if I have a test suite that's got 0% code coverage, then something's gone horribly wrong. Whereas if it's 100% code coverage, I should be elated and very happy with what we've done, and I should be able to code and refactor with more confidence. If you're in the situation, though, however, where you have a very large, complex code base, it's entirely possible that you might not be able to get 100% code coverage. And perhaps maybe that's not something that you should aspire to, because the overhead of designing all of those tests and maintaining them and running them on a regular basis could just be unsustainable or impossible. So if you're in that situation, or you're in a situation where you don't have 100% code coverage, you could still use this code coverage analysis to find the holes where the code is not being tested. And so you as developers who have intimate knowledge of your code will have some idea of where the hot spots are. Where was the code that was particularly difficult to write, where there's a high probability of having a bug? Or where are the portions of the code where people are going to be changing that quite often, so that there's a possibility that people might be putting bugs there as they continue working on a regular basis. So I can run the code coverage analysis and see if those hot spots are well covered by my test suite. If they're not, well, then I can clearly shuffle around my priorities and address trying to get those portions of the code under testing. So there are a lot of different code coverage tools out there. There's Gcov for C and Fortran, which is part of the new compiler collection suite. You compile and link your code with a -- coverage flag, and they suggest that you turn off optimization when you do that. After you've built the code with these flags and without the optimization, you then run your test suite. And Gcov will create some different intermediate files where they're keeping track of which lines have been called and how many times they've been called. And then you can use Gcov or Lcov to create a nice report for you. So Lcov will generate an HTML-based output for you. And nowadays, they also have hosted servers in the form of coveralls and CodeCov, where if you're using something like a version control system and code continuous integration, you can actually have your code coverage analysis pushed off to these servers, and they'll host a nice history of the different code coverage that you have. And we'll see an example of that at the end of the talk. So this, as I was putting together these talks, I just went through and created some toy repository in GitHub. It's down here at the bottom. And Alicia, when she was preparing for this, she created another one called Morpheus, where they have different exercises related to code coverage. And in my repository, I just put some very old code in here. I think some of this code was probably the first code I ever tried to put under automatic testing. And I just ran through, I integrated code coverage with it. And this is what the result looks like if you go to, I believe it's coveralls I was using. So you'll see I have two different files in this portion of the repository, linear function class and modulo mod. What this is telling me is that there are 3 executable lines of modulo.mod, and all 3 of those are being called. So I've got 100% coverage. Linear function class, it's got 82 executable lines, and only 61 of them are being covered, so I'm not doing very well there. I can actually click on this linear functions.class, and it will drill down and give me a listing of the code. The lines of code that have been called are shaded in green. The lines of code that have not been called are shaded in red. And so if you go and you look at this file, what you're going to find out is that my test for this file is a little bit deficient in the sense that it's not checking for error handling. In other words, as I wrote this, I was cognizant that there were certain edge cases. So for instance, I want to check the delta 0, so I avoided a divide by 0 here. But I never actually wrote a test that gave results that would yield that test case. Therefore, none of my tests are actually seeing that my code handles those edge cases correctly and does the error handling in a nice and graceful way. Depending on your projects, that might or might not be important. But there's another caveat with this, which is when you are evaluating an automated testing framework, you can look to see how good they are at checking that errors or appropriate errors have been called. They're not all capable of doing that. And so if you're interested in doing that type of checking, you might want to make certain that you have chosen a testing framework that is capable of helping you out with that. So code coverage is popular. If you're not using C or Fortran, then you can hopefully you can go and find a code coverage analysis tool for your particular language. So we'll finish now with continuous integration, and the short and sweet of this is the goal of continuous integration is to have a master branch that always works. That should sound ridiculously redundant with what we discussed in the morning, and that is sort of purposeful. The idea is that if my goal of continuous integration has the words master branch in it, then fundamentally continuous integration is rooted in the notion of working and collaborating through a version control system. That is the idea of it, the fundamental idea. And so, not surprisingly, the first way that you can move towards continuous integration is by adopting a Git workflow so that you can isolate the master from the integration environment and therefore take a step towards protecting your master branch. However, everything that we discussed in the morning is not quite sufficient. That doesn't really put the continuous into continuous integration because, for instance, we didn't put in any sort of rules that help to minimize the likelihood of having a merge conflict in the first place. And that's what continuous integration is going to do. And it's also going to mix in the notion of testing so that when we do make changes in our version control system, it will trigger these build and test cycles and immediately call our attention to the fact that we've broken something. So if we look into this a little bit more in detail, we can try to realize that one common sense extension to our workflows from the morning is to insist that people commit and integrate often. That's really what the continuous and continuous integration means. And so a motivating case are these two graphics down here. So on the top, we have 2 developers working in parallel, each on their own branch. We can see here that they're doing a substantial amount of work, so 10 or 12 commits, I believe. We can imagine that's a month's worth of time, for instance. As you're already familiar with, we get a race condition, so dev 1 is happy, and dev 2 is going to suffer here. Because they did so many commits in parallel, because they took so much time to synchronize and integrate, there's a very high probability that there will be a merge commit happening here, or merge conflict happening here, and that dev 1 and dev 2 will have to sit down and work together to resolve those conflicts without creating bugs, right? So at this point, this is also a high-risk operation that's going to go on. Whereas if we insist that we commit and integrate often, what we're going to do is ask people to decompose that month-long task into smaller subtasks. And each one of those subtasks will be executed by us as an individual feature branch. And so that's what we see down here. There are constantly race conditions going on here, but these feature branches are short-lived in time and in terms of number of commits and hopefully number of lines of code that have been changed. And therefore, when we do get those race conditions, we're hoping that the likelihood that we have a merge conflict is lower, and also that the difficulty associated with resolving that merge conflict is lower. And therefore, we're less likely to inject a bug as we're working. So on the testing aspect of this, we want to have tests integrated so that we can immediately identify failures. This will clearly have the benefit of increasing the quality of our code. If we consider this integration of testing alongside our new rule of committing and integrating often, we see that we actually like this, because when I push a new branch into my master and I trigger that build cycle, build and test cycle, if it tells me it's failed, well, I know it was only one of 2 or 3 commits where I committed that bug, right? Whereas if I waited a month, I'm going to have to go through and sort back through 10 different commits to try to figure out which one of those have the bugs. And so as David talked about, that's also related a little bit to context switching. If let's say that there's this case where I waited for a month. In the worst case, it was the first commit where I created the bug. Once I found it, I'm probably going to have to go back, reread the code, and restudy it to remind myself what I was doing, which is clearly not a very productive way to work. And so this idea of integrating the tests is clearly related to that test and build server that we were talking about. So we want a system that's going to trigger automated build and test cycles every time we make a change to the code in the version control system. And if we're using these nice collaborative levels, collaborative tool levels of GitHub or GitLab, ideally every time we do a pull request, for instance, we would like the system to run the test suite not on my commit and branch, my last commit and branch, but hopefully on actually the merge product that my merge is suggesting. So my feature branch along with merge. So continuous integration has been around for a long time. There is a growing interest in it. And in fact, you've heard Todd Gamlin talk about it during his SPAC talk, about how they use continuous integration, I believe, to actually monitor the quality of the SPAC core, and how they're working with GitLab CI to try to expand that out so that they can do even more testing of actually the contents of SPAC and what it does. I think there might be a typo here. ECP is working, I'm not certain if it's Travis CI or GitLab CI. From what Todd said, it sounds like it might be GitLab CI, so that we can run our test suites on HPC. And that's related to one of the questions that we had in the morning. So CI, I think when most people think about CI, they are actually thinking about Travis CI or GitLab CI, this idea of the test server. But hopefully you now all appreciate that it's actually more than that. It's the workflow combined with this nice tool that's going to automate everything and going to make my life very easy, because I'm not going to actually be running tests. I'm just going to see if I get a pass or a fail. So there's some setup that's related to this. And as with the test suite, you're going to need to do some maintenance and monitoring. Right? This is clear because when I look at the Travis CI script, I just want to see a green check mark or an red X. I don't want to have to ask myself whether or not I should believe in that. I want to know that my test suite and my Travis CI configurations are well maintained. I just want to see the green check mark and move along. Right? There also are several prerequisites that need to be satisfied before you even think about doing CI. So obviously this should be done in an automated fashion. So I need to be able to have the test server build my system without any intervention on my part or any extra information. I also need to have an automated testing system with hopefully significant test coverage. And I need that automated testing system to be able to feed back to the test server to correctly indicate pass or fail. Finally, if you're running on some of these community systems like Travis CI, in general, they only allot to you, I believe, about 50 minutes time. So you need to be able to know that you can you can run in that time. And what that might mean is when you build your test suite, that you want to be able to bundle up subsets of that test suite. So 1 month you're working on this part of the code. Therefore, you're going to install on the CI system these 3 related tests that will run in 50 minutes. The next month you're working on a different part, so you want to just be able to sort of hot swap out the subset of tests that you're running. So cloud-based CI, this is, like I said, what I believe many people think of when they think of continuous integration. The idea is that these test servers are linked to your version control system. So if you're hosting your code in GitHub, you have Travis CI. If it's GitLab, you have GitLab CI. And so these are automated build tests, systems that will trigger build and test cycles when you, for instance, you push your changes to the remote repository or when you do a pull request. They're run on a cloud system, and you can configure them to run on different environments, different compilers. One of the things I wanted to mention is that these are oftentimes called build servers. The idea is that you're configuring it for the build and execution environment, and then you're just telling it what scripts to run. So in reality, these systems don't know that you're using it for tests. And one of the things that you can do, therefore, is try to sneak in other actions with your script. So for instance, if you're doing code coverage, you can try to get gcov to do what it needs to do the code coverage analysis. If you're actually doing your documentation in something like Doxygen, you can actually have the test server also build your documentation for you. So this is some screenshots I took of that toy repository that I built. I did integrate it with Travis CI, and so what we see here is sort of the root repository if you go to that, and you'll see that there's this .travis.yaml file in here. That's what Travis CI needs so that I can tell it how to build and when to build, for instance. Actually, not when to build. So this is an example of a simpler file. If you go here, it's not the exact same file. This is a simpler one. The first line, what we're expressing to Travis CI is that our code needs to be built in fundamentally a C++ environment, so please build in all the tools you need for that and all the libraries. The next block is telling us, as the way for us to tell Travis CI that we want you to do the build and test cycle on both Linux and OS X. Then finally, we're saying we want you to actually use these compiles, G++ and Clang. And so when Travis CI does the building and test cycles, it's actually going to run on the Cartesian product of that. So for each operating system, it's going to do it with 2 different compilers. And then this is where the action is happening. So in this particular case, it's going to run a make file. If the exit code of that make file indicates success, then it's going to proceed by running this test script. So if both of the exit codes of those 2 scripts indicate success, then Travis CI understands that the build and test was successful. If either one was a failure, then Travis CI is going to declare that that was a failure. Some other things to look at here. This is the integration I was telling you, where Travis CI feeds back its results to GitHub. So here, if we look at the branch view of my repository, we actually see that nice green check mark indicating that my master is in good shape. If you click on it, you can actually drill down and see that Travis CI has run and is happy, and coveralls is happy in terms of the code coverage analysis. And I imagine you all are quite well aware now of seeing these badges around here. So the idea is in my README file, I can link back to the 2 host servers and have them indicate the current results of their different actions. So when I took the screenshot, my test suite was running, and I had 75% coverage. So putting it all together, we're going to go back and revisit that refactoring scenario that we had earlier in the talk, and this time we're going to add on continuous integration. So again, we're going to assume that we have code that's currently functioning, we have test suites, and we're hosting it in this case in, let's say, GitHub. So the first thing we're going to do is create our feature branch called refactor.branch, and then we're going to enter into this blue block, which is refactoring with tests. That is effectively that last workflow that we saw, where we're going to decompose the work into refactor steps and use these lightweight tests to help us execute those refactoring steps to know that we're correct. At this point, we have some reasonable confidence that what we've done is actually correct and perhaps should go into master, and if we do that, it won't break master. So we'll issue a pull request through GitHub to master, and that will trigger within the continuous integration system a run of some test suites that will run within 50 minutes. So at this point, if any of those indicate a failure, well, then I need to go back onto my refactor branch, and I need to go and fix up those steps until, again, all of those lightweight, fast tests are indicating success. At that point, then I'll do a commit and a push the pull request should get updated, I believe, and the CI will redo its run and rerun those checks. And I'll keep going through that cycle until finally all of those tests within that portion of my test suite indicate success. And this is where you're going to start to see some similarity with what we were showing in those Flash 5 workflows. I'm actually going to pause at this point, for instance. Like, let's imagine that this is now, I've got everything not on the master but on the staged. I'm actually going to pause and allow a different test server to execute my full test suite on the staged branch as a nightly test. And again, if those fail, well, I need to go back and loop back around. If not, then I can know with some fair confidence that my code is correct, and therefore if I put it into, merge it into master, I won't break master, so I would actually accept my pull request into master, at which time we would jump up and down because we've done a good job. So it looks like I mismanaged my time a little bit. I really thought I needed to jettison those 3 lessons learned cases from the beginning, but it turns out that I finished much quicker than I anticipated. So that's a benefit for all of us then. Does anyone have any questions? Yes?
Could you explain how the code coverage is detected in a little bit more detail?
In terms of how it's detected?
Yeah, how does it know that some of the parts are covered and not exactly?
So in terms of how gcov does its internal work, I really don't have any idea. So the idea is that somehow we pass this // coverage flag in, and it knows that it needs to do some extra work. The idea of turning off the optimization is that our end goal is to have, if we go and look at our code listing, is to have a number next to each line indicating how many times that line was actually run. So we want to actually turn off the optimization. So I believe gcov needs that so that it can do that mapping back onto the listing in the easiest way possible. If you go to the gcov page, it's actually going to tell you that you need to put in 2 flags to do this. But I believe this -- coverage, I searched for it, and I think on Stack Exchange they say that that's actually an alias for it. It's fairly simple. It's nice to use and effective. Yes?
So you can think of the infrastructure that does this as essentially the same kind of thing that you described with the asserts.
Okay.
Right? It tracks whether the asserts are satisfied or not. Right? It's just you break the code up into basic blocks, and you count has that been tested or not. Right? If it's been executed, then you say, yeah, that's good. If it's not.
Any other questions? Yes.
This is not a super technical question, but it also has to do with getting people to use the Git process they use. If you have people who don't want to follow this detailed plan that you put out, do you have any tips, or are there ways to make it easier to follow than to not follow it? Like, do you have any automated tools that actually prevent them from
In terms of?
committing to whatever branch they feel like?
Okay, so when we first started doing the Flash 5 workflow, I wanted to have this idea that people's branches would be their individual branches, and so that people wouldn't be basing their branches off of mine. Part of that was because I wanted to use the rebase. So I don't know, again, I said that rebase is something that's kind of dangerous. The idea is that if you do the rebase internally to your local repo, like we were doing in that example in the morning, everything is fine. If, however, you publish a branch to someone else's repository and you try to rebase that, you can have very serious problems, because if someone else based their branch off of yours, you just moved it out of the way. So what happens to their branch? That can cause a lot of problems. And so I wanted to have the confidence that no one else would base anything off of my branch so I could rebase. 5 minutes later, I think someone else was already violating that. So the end result is we got rid of that rule. So as long as, a caveat to that is the person who did that understands Git better than me. And so he did that in a very intelligent way, right? I'm not particularly worried about him. He's not going to cause any problems. I'm the one who's going to be causing problems, more likely than not. I think the reality is that you have to sort of like I said in the Git workflow, is start off with the simplest, let people gain experience, appreciate that the extra overhead is actually worth the effort, and then just start ramping up the complexity as people start to accept it and like it and appreciate that. Does that make sense? Yeah. Yeah.
Could you use permissions?
Hmm?
In any way keep people from screwing up?
So I do know that other people, for instance, you can protect master, I believe, in GitHub. So you can actually say that the only people who can alter it are these 2 or 3 people. And so, for instance, what you would do is set up a system, therefore, as part of your policy, that everyone has to do a pull request into master. And then you have to wait around for those people to review your code and accept it. So a couple comments about this is that you want to make sure that your policies are easy to learn and use, but you also want them to be easy to enforce. Another part of this is if you keep going to the extreme on continuous integration and you just, every feature branch that you create only has 1 commit, and you're doing 5 pull requests a day, and there's 10 people in your team doing that and 2 people approving your pull requests, well, you can imagine that that's going to be a very serious bottleneck. So part of doing this is really looking at the whole picture and trying to figure out how you can get to the balance points. Of course, you're not going to get there on the first try. You're probably going to have to iterate in time. Any other questions? Yes.
So I always find very hard to choose the tolerance of
It is hard, isn't it?
yeah,
Okay.
very hard. And so that's why I wanted to ask you if you have some more suggestions on some experience. I understand that it's very case specific, but do you have some experience to share about it?
So for right now, on most of the projects I'm working on, I'm the one who's maintaining the baselines. And I'm very fortunate in the sense that I can demand bit-by-bit exactness. That is very painful. It gives me great comfort to be able to program having that exact baseline, that 0 tolerance, but it is quite painful. One of the benefits that I do see from that is that every time I do make a change where I have to reassert a new baseline, I keep a table of those changes. So which commit that happened. I'll actually keep a table of how the metrics changed. And then I also have a written history where I'm writing down what changes I made that could trigger that difference in round-off error and why I believe that's correct. And so what I'm doing with that now is once I've seen, I've recreated, let's say, 10 different baselines, well, now I'm starting to get some general statistics, getting some understanding of where those tolerances are. So I suppose one way of doing this, if you don't have that determinism in your code, is to keep track of the table. Do your best effort to establish that this is correct. Or, for instance, if your test suite declared a failure, but it really wasn't, boost your tolerance up a little bit cautiously, let's say, but keep a record so that you're starting to get an idea of what is the natural level of the round-off error in your calculation. Unfortunately, I can't do better than that. I don't have any ideas. Yeah.
Diagnostics that you would have typically built in. For example, if you are using the conservative formulations for various physical quantities, then in addition to looking at the your baseline, you can look at if all those quantities are conserved or not, and that can give you a hint as to whether that is a drift or a real error. And so there are those are some of the, like you said, there isn't a standard answer to everything, but there are ways of getting around this problem. And the other thing is, of course, knowing your error bars really well.
So just out of curiosity, did your opinion about your effort that you put towards automated testing, has it changed at all? Or are you still in the same state?
No, I think it really depends on the scale of the project.
Yeah.
Most of the daily things I do don't require extensive testing. It would be good to have them, but just the time scale on which I'm required to provide results don't allow me to test all the schools.
Any other questions, Jeff?
I just have a comment on the earlier question about how to sell Git to other teams who are uneasy about adopting it. I've had this essentially do the same thing and sell Git to a couple of teams at Oak Ridge, and in my experience, the 2 big sellers are the history that comes with it, right? So the little timeline, the linear timeline of commits doesn't go away for the lifetime of your project. So if you want to go back to exactly this one individual commit from 4 years ago, that's fun. So that's one seller for a lot of people. And the other seller for teams is kind of the ecosystem that you can tie in Git to. So whether that's like DipChat or probably Slack as well, whatever your team uses, you can integrate with things like GitLab and GitHub, such that you can improve the communication across your teams. So if I open an issue, I can tag you, and maybe that pings you on your phone and wakes you up in the middle of the night.
It's not so much getting them to use the tool as getting them to use the tool in a consistent manner as everyone else on the team.
Well, I guess that goes back to enforcing
If they've already figured, be like, this is the best way to do it. And then,
Well, so I already told people a story is that I learned about version control system many years ago, and I just did not see any reason why I should invest the time in learning about it. And so I just kept putting it off. And by the time I actually sat down, I think I learned SVN, I felt like a complete moron because I realized how much more difficult I had made, let's say, those last 10 years. So part of the problem is that sometimes we don't know that we're suffering, right? I say that's from personal experience. And so that might be something that you can do, is point out to people like, hey, there is a better way to do this. If we had all worked together more consistently as a team, perhaps we wouldn't be in this sorry state. Any other questions? Oh yeah, another one.
And for example, for codes that have lots of different cases, for example, you just let's say turn a flag on and off, and you have 10 different cases, 10 different scenarios. How can you get a good coverage index without running the test suite for tricks?
So that's where you would hopefully like to zero in on unit tests. So it depends. If this branching structure within a function or a class, hopefully you can write a unit test that's going to do very simple, quick tests over all the different possible pathways through that code. If, however, this is existing sort of outside of the function and class level, where you're talking about having a very modular, encapsulated program where you can swap out all the different units, well, then you can start looking at that coarser level where you have the subsystem tests. The idea is that when you have this hierarchy, you're really trying to put at your disposal the right tool for the right job, right? So in terms of locality, what portion of the code are you testing, and also how quickly I can use it. So I don't know if that answers your question. It depends to some degree on where, really where that conditionality is being implemented in your code. Otherwise, if it's really at a system level, well, then I think you might need to start looking at what Anshu was doing in terms of that matrix. Right?
Yeah, and sometimes you don't have to rerun the test also because you have enough information within that set of tests that if you can reason about this part is tested in this test, this part is tested in this part, and if it's working right here and not working right here, then it has to be this section. That kind of reasoning about can lead to better coverage also, and that's part of selection of the matrix.
All right, well, thank you all for your attention.